Hey guys, Buildzoid here, and today we're going to be taking a look at the Gigabyte Z590 Aorus Tachyon. Currently my favorite motherboard of all time, because, like, in terms of overclocking features. Unfortunately, the LGA 1200 socket doesn't really have enough PCIe lanes for me. But yeah, in terms of like overclocking functionality on a motherboard, it doesn't get better than this right here. Also, Gigabyte gave me this board, so now I sound like a massive shill because you got a free motherboard, and of course it's your favorite motherboard of all time, but, um, well, I've not used any motherboards that are better, so what the hell am I supposed to do about that? Right? Like, so, yeah. So that's kind of unfortunate. Like, if I had, because there's a few other boards that I can think of that could maybe challenge this board for the title of my favorite motherboard of all time, but I don't have the others. So, yeah, that's kind of that. And also, some of the others aren't even released yet, so it's just like I'm not sure really how I'm supposed to do anything about that. But for now, yeah, this is definitely my favorite motherboard of all time. So let's get into why I think this is such a great board. So, starting off with the rear I/O, and this is one of the places where I kind of have a nitpicky, like, I wouldn't put this where it is. So you get Q-Flash Plus, which, fine, whatever. That allows you to update the BIOS of the motherboard without even having a CPU installed. That being in the rear I/O, I don't really care. I don't really, like, I think if it was internal, it wouldn't really make a difference either, but yeah, there's no real harm in having this on the back. The OC ignition switch, on the other hand, is one of those things that I'm like, why isn't that internal? So Gigabyte, for some reason, is saying that you can use the OC ignition switch for like testing your water cooling loop. But what the OC ignition switch does is it keeps your power supply running while the motherboard is turned off, which is useful if you're running an LN2 setup and you have like fans that need to keep going all the time. But this is, or in some cases, you also sometimes have like extra extra accessories that you might be running off of the PSU. So you might want the power supply running constantly, even if like the motherboard isn't running. But you wouldn't use this for water cooling testing because if the power supply is running, then you've got 12 volts at the end of every single 12-volt power cable. And the biggest risk with a water cooling leak isn't that it's going to short your like V-core or memory power or whatever. It's that it's going to short your 12 volts, which is still present because the power supply is running. So I have no idea why Gigabyte is like, yeah, this is for water cooling testing. Like, no, the original reason why they introduced this was the LN2 overclocking scenario that I described, and they introduced it with their like extreme overclocking focused Z87 boards. So yeah, this isn't for testing water cooling loops. That's a stupid idea. And the other issue I have with it is like, why is it on the back? Like, it's a switch. You don't, like, if you put this motherboard in a case, this isn't really a function you're going to be using very regularly. And if it's on a test bench, well, I mean, it could have been, alongside one of the other switches over here. I would have much rather seen either clear CMOS on the rear I/O or limp mode. Actually, what I would have done is like clear CMOS and then limp mode under it. Which we'll get to what limp mode is soon enough. Anyway, below that we have PS2 ports for Windows XP support, because Windows XP is the fastest operating system for some benchmarks, and unfortunately Windows XP, being very old, just doesn't know how to work with modern USB ports. So you need PS2 ports as a workaround for that. So that's what those are for. Then we've got, some USB ports. There is only 7 Type A's, and I'm more of like a 8 Type A USB port person, but the thing is, there legitimately isn't any extra, like, there isn't space left for more USB ports here, so, yeah, like, I would have axed the Wi-Fi and added more USB ports, but for some reason, people want Wi-Fi on their systems. It's a desktop system. Like, it's an EATX motherboard. Stop pretending you're going to be moving it around and run a bloody cable. It's better for your internet connection. Anyway, yeah, but you do get Wi-Fi, and that Wi-Fi is, what is it? It's the Intel Wi-Fi 6E, and then you get 2.5 gig Intel LAN. So that's the rear I/O. You get dual 8-pin power connectors, which on a motherboard meant for extreme overclocking of 11th gen and 10th gen CPUs is totally reasonable, because on liquid nitrogen, they do pull more power than what a single 8-pin is really good for. like technically you can shove, like you can go out of spec temporarily on these connectors, right? Because the concern with going over spec on connectors is like, well, you'll melt them if you stay over spec for long enough. But most extreme overclocking scenarios, you don't have benchmarks that last that long, so you can kind of get away with really blowing through the specification of the power connector, which is like how AM3 Plus motherboards get away with having single 8 pins regularly. Um, but yeah, honestly, like it's just better to have two 8-pin power connectors, like if the space is there. Also, Gigabyte is using the solid metal pins instead of the folded metal pins, which means that the connector can handle more current. So each of these power connectors is good for 480 watts, assuming you're on 18 gauge cabling from your power supply. If your power supply doesn't use at least 18 gauge cabling on the 12-volt power lines, your power supply is garbage. I'm serious, like, there are PSUs that do cost saving by using under-spec'd cables. Also, you can get cable extensions that are under-spec. So, also garbage. Anyway, so that's this side of the board. Now let's get over to the much cooler side of the board. The side with the power button, which we've seen before, the reset button, which we've seen before, and the greatest button ever made, limp mode. So this is Gigabyte's version of Safe Boot, and I must say they managed to implement, like, the thing is, I like Gigabyte's limp mode implementation a little bit better than, say, the Asus Safe Boot or even MSI's version of Safe Boot, because Gigabyte's just takes you to the BIOS. Like, there's no splash screen going like, hey, you're in safe mode. No, it just goes straight to the BIOS, which is like that's a really minor nitpicky thing, but I have so many motherboards that it's just one of those things like, well, that's a nice touch that I don't have to like hit, like I can let the board boot up and it'll go to the BIOS. I don't have to, go through the whole like confirming that we're in safe mode with F1. So that just, shaves off a couple seconds off recovering from a bad overclock. And what the limp mode and what safe boot is, because if you don't know what Safe Boot is basically when you boot up, it boots with the stock settings, but it keeps all of your BIOS settings in place. So you don't have to use the clear CMOS switch if you screw up some of your overclocking settings. You can just hit limp mode, which means basically for me, I use this button more than any other button on any motherboard that has this button. Actually, no, that's not true. There are some motherboards where the Safe Boot implementation is kind of clunky, so I don't end up using it that much, but yeah, especially on this board, like I've been using the Safe Boot button so much. Like honestly, I would like they should have given it the nice big button. Anyway, below that we've got clear CMOS button, and I'm not a fan of the position of this. Like I'm really surprised that I've not accidentally hit the clear CMOS switch while working with the board, because it is right next to the limp mode button, and like I would have maybe moved it here. Just put it ever so slightly further away from the limp mode button, because you might slip and hit clear CMOS, and then you've just kind of negated all of the benefits of the limp mode button if you accidentally hit clear CMOS. But like that hasn't happened to me yet, but it's something that I could totally see happening, and it's just like I'd put the button further away for that reason. But like so far, like it's not been an issue, which is why I'm not like. Why I feel like I'm being super nitpicky with that, but it's true. It's like just like I'd put it further away. It makes more sense to me. Anyway, next to that we've got the retry button. So this is a hard reset. So you can actually crash the CPU so hard that the reset button stops working. In that scenario, the retry button does still work. You press that, it shuts down no matter what. And the utility of this is, well, if you hard lock up the system, you can still force it to reset. And also, if you're doing memory training, there are certain, if you're running really hard memory settings, sometimes you won't be able to train them. So you can hit the retry button to get the memory controller to go through the training process again. And maybe next time it doesn't screw up and you actually get into the operating system with whatever memory overclock you're going for. So yeah, very, very handy if you're pushing like really hard memory overclocks. And then below that, we get even more buttons. So we've got the A and B buttons. These are for loading up BIOS profiles. So, if you do use the clear CMOS switch, you can use one of these two. I'm assuming the main idea behind these is if you're like on LN2 and there's like some specific voltage levels that you need in order to boot, then you can save a profile with those specific voltage levels to either the A or B button. You'd probably want to have like one button permanently on like a safe LN2 profile, and then like the second one for like your hot profile in progress kind of thing. So yeah, anyway, Yeah, so you can use those for booting up with starting the board with a profile already loaded, which is kind of neat. I've not yet taken advantage of that, but yeah, it's like the thing is like you could just keep mashing limp mode like I do, and just never save a profile in the first place, you know. That's my approach currently. But anyway, next to that we got the ratio up and ratio down buttons. These also function as BCLK up down. Currently, the way you switch between the BCLK control and the ratio control is through the BIOS. But there is this switch over here, which currently doesn't do anything, but I've suggested to Gigabyte that, like, since this switch currently doesn't do anything, it could be used for controlling the functionality of these two buttons. And what I really, really like about the way Gigabyte has implemented the BCLK and ratio control is that you don't need to you don't need to install any software. Like, there's a lot of motherboards with, like, hardware overclocking buttons like this, and way too many of them require you to install, like, chipset drivers, then some random overclocking utility, and then another overclocking utility to actually get the buttons to work. And it's just like, you know, like, why is it that Gigabyte's motherboards never need that much garbage installed to get the buttons to work? And yeah, so this is one of those unique things about Gigabyte boards that I'm a huge fan of, is because this isn't the first board where they've done this. It's just that they don't regularly sell boards with plus minus, like, these ratio up down buttons. So it's kind of like, whoa, yeah, this is the better way to have this implemented compared to having to install all kinds of software just to get this working on a lot of the other boards. So yeah, it's a very nitpicky thing. Like, you just have to install 3 utilities, but, like, come on. Like, you just have to install some stuff on other boards, but, like, it's just better if you don't have to install stuff in the first place, especially considering that it is evidently possible to implement it that way. Anyway, below that we've got the post code, which is, you know, for your usual, all your troubleshooting needs. And if you have a motherboard with a postcode and you're doing memory overclocking, I highly recommend that you actually watch what the postcode is, like, showing as the board is booting, because that way you figure out what, like, if you're doing something wrong or right. So anyway, next we've got all of these switches over here, and we're going to go from the bottom to the top because they make more sense in that order. So here, actually, wait a minute. Do they make more sense? I can't. This should be, yeah, okay, so this is BIOS select. So this being a high-end Gigabyte motherboard, you of course have dual BIOS on it. So this switch chooses which BIOS chip is active. This switch allows you to disable the automatic dual BIOS mode that Gigabyte has, and you do that by putting the switch in the number 2 position, which you'll notice I already have it in the number 2 position because Gigabyte's automatic dual BIOS is incredibly frustrating, which is why all of their high-end boards have it, you know, have a switch to disable it. Funny how that works. Anyway, so yeah, you can disable the automatic dual BIOS, and then if you want to like switch between the BIOS chips, you just use the other switch. Dual BIOS is super useful. Like, for one, if you break a BIOS, that's one part. But the other thing is, if you're just testing different BIOSes for various overclocking capabilities between BIOS updates, it's super convenient to just have a second BIOS chip that you can throw, you know, the new BIOS you're testing onto, test it out, and it's like, okay, and if you like it, you can just stay on that BIOS chip and keep using it. And then if there's another BIOS update in the future, you can put that on the other chip, right? And again, run your comparisons. And so this is a really cool feature, in my opinion. And every, like, overclocking focused board should have dual BIOS, in my opinion. Anyway, above that we have LN2 mode, which basically preloads a bunch of voltage settings for LN2 overclocking. The board doesn't come with any voltage restrictions, which is pretty so on a lot of other boards, LN2 mode lifts a bunch of voltage restrictions, but Gigabyte is like if you get a Gigabyte Extreme overclocking board, there's no restrictions ever. So this literally just preloads some extra settings for you, which, like, I like, but the thing is like, you do have to, like, if you accidentally punch in a too high voltage, like 2 volts, and try to boot with that at ambient, you're going to have a really bad day. Though, to be fair, most other motherboards let you punch in voltages high enough that you're going to have a bad day anyway, so, you know. It's not really, like, I don't really consider that a huge downside. But yeah, it's one of those differences where this doesn't actually, like, unlock any extra voltage range, which I appreciate, because on some boards, like, the non-LN2 mode voltage ranges are actually too low. Even for ambient overclocking, they're just too low. So yeah, anyway, so that's the LN2 mode switch. Next to that, we have the reserved switch. That currently doesn't do anything. It might in the future be used for controlling if these are BCLK or ratio. Then above that, we've got LN2 offset, which is like even more LN2 overclocking voltage presets. And then next to that, we have the, what is it? Trigger switch, right? Slow mode. Most other vendors would call that slow mode. Gigabyte calls it trigger. Gigabyte just likes having unique names for stuff. Anyway, so the trigger switch, what it does is it puts the CPU to the lowest possible ratio for both the core and the cache. This is very useful for, like, if you're sitting on Windows desktop just messing around with, like, organizing your screenshots or you know, setting up a benchmark to run. Really convenient for that. It's also useful if you're, like, there's a few benchmarks that are easier to run than, like, the loading screen, like, than the loading screens are for them. So if you're on a, like say you're opening CPU-Z, you can actually run, say, SuperPi 1 million at frequencies that would crash on CPU, like opening up CPU-Z. So what you would do is you would go into slow mode, open CPU-Z, and then when you're about to take your screenshot, disable slow mode. Yeah, and then there's other things like, well, actually, you can sort of use the ratio up-down buttons for that. Like for 3D Mark, the actual process of loading the 3D Mark benchmarks, the ones that use System Info. System Info is like an all-core, very hot I think it's AVX workload. So you can actually like you can underclock the CPU just for that, for the loading screen, and well, for the like system info verifying system details message. So you'd underclock for that and then raise the clocks as soon as you get to the the Firestrike loading screen, which is a thing I've legit done on water cooling. Yeah, because my 6950X was not happy about running, what was it? I think 4.5? Or I think it was 4.55 for Firestrike. Like I couldn't get if Firestrike was running, it was fine, but like the part where you start Firestrike, not happy about it. So yeah, or you can use the trigger switch. The thing with trigger is that goes all the way down to like 8x CPU clock and 8x uncore, so your CPU ends up super slow, and so you end up spending a lot longer on the loading screens, which is why you might want to use this instead. But this is also great for like lowering your power consumption at idle if you're on liquid nitrogen. And again, just like messing around with files or whatever. So yeah, that's a really useful feature to have for LN2 overclocking. However, it is worth noting that like flicking that switch on and off on Intel CPUs triggers a pretty nasty voltage transient, so you don't really want to be using it for like CPU-Z validations. It's not going to be super helpful for that. In fact, it might make the system crash if you're right on the edge of stability. But it's great. Like if you have a relatively stable multi-core overclock or something like that, it can, you know, it's useful if you suddenly have a workload that you kind of need to run, but you don't want to run it at full speed. Anyway, so that's sort of all the switches and buttons. You've also got a massive array of voltage read points. The one thing that's missing from these is VTT-DDR, which I don't think is a huge deal, because honestly, like, I never use voltage read point. Like, I generally don't use voltage read points. They're one of those things that you'd think that you'd be using a lot, but really you don't, in my experience. Like, yeah, I really don't use these that often. You also get 3 voltage read points for just vCore. So you get vCore die sense, you get vCore socket sense, and vCore at the super IO. I not like so that's neat, I guess. If you want to compare your voltage readings against motherboards that don't have die sense, then yeah, you can use the socket or super IO reading there. Not like, again, I'm not entirely sure why, but yeah, you've got your 3 voltage read points. Like the thing is you like voltage read points are useful, I guess, if you're troubleshooting or something. And on that note, yeah, like I think VTT DDR is missing. Or if you're, because the thing is like on a motherboard, you can just go into the BIOS and check if the voltage is roughly where it's supposed to be, right? Like that's the thing, is like being off by 10 millivolts is not really that big a deal. And yeah, sure, the BIOS might be reading a little high or a little low, but it's like it does, as long as you like the thing with voltages with a lot of voltages is like it's more about having the ability to change them than it is about knowing exactly what they are, unless you're like moving memory sticks from motherboard to motherboard and need to make sure that the voltages are the same so that you can run the same settings. But yeah, anyway, so you do have voltage read points for basically everything except VTTDDR, which, I mean, I think that should have been present. Like, considering all the other ones that are available, that should have probably been included as well. Anyway, then we get these very weird SATA ports over here. These are for Windows XP support because Windows XP not only doesn't like modern USB ports, it also doesn't like modern SATA controllers, like the ones in the chipset. So there's a SATA controller here that's compatible with Windows XP, and you can run Windows XP off of those SATA ports right there. And then we get this USB port over here, which is for like saving benchmark scores. Like, this is just a USB port that you can easily access if you have the motherboard on a test bench. That's all it's really for. And Gigabyte has done that on some of their OC boards in the past as well. So yeah, you just get a USB port over here. So I guess for test bench applications, you do technically get 8 USB ports built into the board directly, which is kind of neat. Anyway, right-angled 24-pin. Well, screw it. Let's talk about it. Like, the thing is, this board is very, very, very low production volume. So I don't think there's a very high chance of anybody actually trying to put one of these in a case. But if you somehow got your hands on one of these and then decided to put it in a case, it is very EATX, right? Like, you can see right here, it's wider than an ATX board, and then with the right angle 24-pin, well, you can imagine where the 24-pin power connector is going to end up being. So that's something to watch out for in terms of case compatibility if you somehow manage to get your hands on this board. Because from what I've heard, if you don't already have one, you probably won't get one. Because I've heard that apparently most of them or all of them sold out. So yeah, good luck finding one of these. And I really doubt they're gonna make more. But who knows? Maybe they'll decide to make more. It would be cool if they decided to make even just a couple hundred more would be neat. But yeah, I don't think that's very likely. Anyway, let's move on to the power delivery. So, the VRM on this board is not the most powerful VRM in Gigabyte's Z590 motherboard lineup, but it is, however, like what I would consider just right for every CPU that you could put into the LGA 1200 socket. So, we've got an 11-phase V-core. And then a single-phase iGPU over here, which I'm not even going to bother writing out how many phases that has. And then you've also got one phase of system agent down here, so SA. And then you've got like your 2 different VCCIO rails, and there's like LDOs all over the board. Actually, oh yeah, there's a bunch of LDOs hiding under this PCIe slot. This PCIe slot is X4 off of the chipset, by the way. But yeah, there's a bunch of LDOs hiding under that, and that's just for like the extra voltages that you might that don't really need a lot of power, but do need to be present. Well, the thing is like if you get low end enough motherboards, these won't actually be separate regulators because they all sit at like the same voltage. But for LN2 overclocking, you might need to run those minor rails at different settings, and that's why we have like a larger array of LDOs down there. Anyway, yeah, so 11-phase V-core, 1-phase SA, and how do I want to do this? This is kind of awkward with the whole, like, it's not the most powerful VRM on Gigabyte's Gigabyte Z590 lineup. Like, the thing is I like the priorities with the design of this VRM are just very different from what your regular like consumer motherboard design priorities are. So the priority with this board was to get the best possible voltage regulation. Well, I screwed up that sentence. We'll just keep going because I'm sick of trying to reshoot this video. So yeah, basically the goal with this VRM was to get the best possible voltage regulation no matter what, and that means no doublers. Because doublers add a very small amount of delay to the PWM signal going from the voltage controller, which in this case is a... Where do I want to put that? Let's just write it right over here. ISL 69269. which, like, this is the same controller Gigabyte was using on their Z490 motherboard, so that's not a new controller. It goes all the way up to 12. Like, it's a 12-phase controller, and here it's running as an 11+1. So you've got your 11-phase V-core from that, and then you get the +1 for the system agent down here. And yeah, and there's no doublers, because if you had doublers, they would add a very, very small amount of delay to the PWM signal. And the problem with adding that delay to the PWM signal is that it gives the... Because basically, your VRM responds to the current demands of the CPU. So if the CPU, and actually, it's like the CPU doesn't demand current, it's more like the CPU has a certain level of impedance, and when that level of impedance goes, like, drops, the amount of current that your VRM needs to supply in order to maintain the voltage at the same level goes up. And so basically what happens is your CPU's impedance drops. The current, so now the voltage starts falling because the VRM doesn't magically just output whatever amount of current the CPU demands whenever it demands it. So the voltage starts to drop, and then the controller notices, hey, the voltage is dropping. So then the controller sends out a changes the PWM signaling to all of the power stages. And if there's a doubler in between the power stages and the controller, well, then that change in the PWM signal gets delayed going through the doubler. This delay is very, very small. It's so small, in fact, that when I was testing Z490 motherboards, I literally couldn't measure a difference between the transient response. And that, admittedly, I was using just an 8-core CPU, not a 10-core, but I don't think that... Like, the thing is, a 10-core would only pull, like, 25% more current than an 8-core, and that's assuming I was able to run it at the same voltage, which is kind of unlikely. But yeah, on Z490, when I was testing the boards, like, there was no measurable difference between motherboards with doublers and without doublers. Like, it was impossible to get a... Admittedly, my oscilloscope only goes to like 10 millivolts of resolution, but yeah, I couldn't measure a difference. So, like, if your VRM is designed, depending on how the VRM is designed overall, the presence of the doublers doesn't really make much of a difference, but technically it is better if you remove them. Like, because the PWM signal can get to the power stages ever so slightly sooner, which means the voltage, because the voltage continues dropping while the controller is trying to, you know, get it to come back up again, or while the controller is responding to the transient from the CPU. So, because of that, like, if you remove that delay, you can get a slightly lower... like, you can slightly improve the undershoot and the overshoot of the VRM during transient response. Now, other than that, so step 1, remove all the doublers, minimize the delay between the controller and the power stages. I don't really think that's enough to make a measurable difference, but the other thing that Gigabyte did compared to their Z490 VRMs is they added all of these pulse caps to the output. Now, admittedly, some of them are for the iGPU, so we have all of these pulse caps from Panasonic, and then they've also added a whole bunch of them to the input. I'm really surprised about the decision to go with a bunch of SMD tantalum polymers for the input filtering, because generally the input filtering doesn't really matter that much for transient response. Like, yeah, like, in my experience modding, like, GPUs, it basically doesn't matter what you put. Like, what you can have arguably garbage coming into the VRM, and as long as the output filtering is good enough, you could probably deal with it. So I'm kind of surprised that they decided to upgrade the input filtering, but hey, maybe that's necessary to get results in this case. But yeah, the big difference compared to the Z490 boards that that I tested is that this doesn't have any through-hole capacitors in the output filter. It's all SMD tantalum polymers from Panasonic, and the big advantage with these SMD capacitors is that they have much lower ESL than your regular through-hole capacitors. So that's the impedance. That's the equivalent series inductance of the capacitors. And basically, the way you can think about it is similar to how the whole reason you actually have a transient response problem with a VRM is because you have these inductors in the way of the in the way of the phases. Without these, the VRM wouldn't function. So they're not optional. It's just kind of like you gotta have inductors. That's just how buck converters work. But the thing is so each capacitor basically has its own in-series little a small amount of inductance, and that means there is a limit to how quickly the amount of current flowing in or out of the capacitor can change. So obviously when the CPU suddenly goes low impedance and starts demanding a whole bunch of current, well, you want capacitors that can very quickly ramp up to the amount of current draw that the CPU is suddenly demanding, assuming that you want to have good transient response. Of course, you could use cheaper capacitors if your goal is to just meet the minimum specification set by Intel in their design guidelines, which is really low. Like, there are motherboards with like 3 output filtering capacitors in total, and this is just like, I can't believe that functions, but yeah. This is not a board like that. So basically, yeah, these are, like, these are expensive capacitors that make the voltage regulation better. And hopefully, and then Gigabyte also still has like some of them in the actual CPU socket cavity on the back, and then you also have some little multi-layer ceramics scattered around the VRM as well. And of course, on the front side of the socket, we do have all the multi-layer ceramics in there directly. So I'm kind of hoping that this will be like the first motherboard that I've tested that actually performs significantly better than Gigabyte's Z490 motherboard lineup. Because in my testing, like for the VRM testing, like the transient response testing I did for Z490, it was like all of the boards basically performed the same, which is kind of disappointing. But admittedly, I was only testing like, well, no, even like Gigabyte's $220 Z490 motherboard had perfectly good transient response. So I'm kind of hoping, and like transient response on par with like the Z490 Extreme that Gigabyte made. So I'm really hoping that this switch to like, well, getting rid of the doublers and then then switching the entire output filter and the input filter to just SMD polymer capacitors instead of using, because like the Z490 boards had like a mix of through-hole capacitors and the polymers, but this is just polymer. Well, technically the through-holes are also polymers. SMD capacitors. Like the main difference is physically just how does the capacitor attach to the board. That's what changes the equivalent series inductance. So anyway, yeah, this is all SMD capacitors for the output filter and the input filter. Hopefully that's enough to actually make it like register on my oscilloscope, because like I am planning to get an better oscilloscope eventually, but yeah, I'm still stuck on the one that only has like 10 millivolts of resolution. So I am not sure if like if this doesn't manage to get a better results in testing, then it's like, okay, I think Gigabyte managed to hit the limit of what the LGA 1200 socket is capable of doing with their Z490 boards. Because at the end of the day, right, no matter what you do with the VRM, you still have the inductance and the resistance of the CPU socket between the VRM and the like the CPU. And so, yeah, like you could have the world's fastest, like at some point, you're just going to hit the limit of what the CPU socket can do. And it's actually really interesting if you look at like transient response on like the really massive server sockets. It's somewhat better than what you get out of the mainstream sockets just because they have much higher pin counts. Though I guess if you had a high enough power draw CPU, even with that many pins, you could potentially hit the limit of the socket eventually. Like you could eventually be socket limited anyway. And then of course GPUs don't use sockets at all. They just use BGA, which BGA is even better than like BGA is better than any socket. Because you don't like pins aren't really, great for carrying current. Which is why you need to have so many of them. And even then, like, CPU sockets lose quite a bit of power. Like, even for just DC loading, sockets lose quite a lot of voltage. Just getting from, like, the motherboard to the CPU socket. And then the CPU substrate itself is also not exactly, like also has resistance and impedance. So yeah, there's a decent chance that like this board, this board is going to be entirely limited by the capabilities of the CPU's own substrate and like the socket itself. So, yeah, but this should definitely be one of the best, right? Like the thing is, like Gigabyte already had like one of the best best VRMs for voltage regulation on Z490, and with Z590, it's like, well, hopefully there was room for improvement because with Z490 it looked like there wasn't. So we'll see if this board manages to push, get even better voltage regulation. But I'm kind of worried that like Z490 already hit the limit. Anyway, Yeah, so Gigabyte prioritized voltage regulation, and that's why this isn't the most powerful VRM in their lineup, because it's just like they got rid of the doublers, and that's actually most of it, is just getting rid of the doublers. Well, the other option was to like mash a bunch of power stages in parallel, but then the VRM wouldn't fit on the board anymore. And honestly, I think this the thing with this not being the most powerful VRM on Gigabyte Z590 lineup is it's not an issue whatsoever. They're using Vishay Semiconductor SiC 840 smart power stages, and these are 100 amp. Well, the nominal current spec for these is up to 100 amps smart power stages, and honestly, on paper, these look worse than the 90 amp power stages from Intersil. Now, there is a problem with like, how does Intersil test their power stages? How does Vishay test their power stages? How does Infineon test their power stages? How does On Semiconductor test their power stages, right? Like, there's going to be different test methodologies and different measurement methodologies, and so comparing data sheets not really that great. But the thing I'm more annoyed about than the fact that I don't know why Gigabyte bothered with the 100 amp spec. Like, if I was in charge of this board, I would have used the 90 amp Intersil parts. It wouldn't make a difference. Yeah, it either wouldn't make a difference, or it would actually be more efficient, assuming that, like, if Intersil's test methodology is comparable to Vishay Semiconductors, then the 90 amp Intersils are just better than the 100 amp Vishay Semiconductor parts, which is like the and like Gigabyte uses the 90 amp Intersils on all of their other boards. So I guess like the logic for using these parts that are like 100 amps nominally is that, like, because the VRM doesn't have a very high phase count, they were gonna, like, for marketing purposes, you want big numbers. So let's go find a 100 amp power stage, but it's just like, on paper, this one isn't even good. Like, yeah, it's 100 amps nominally, but you're never gonna use a power stage as its nominal current spec, because that's stupid. None of them are usable at their nominal current specs. Like the 90 amp parts, you don't want to run them at 90 amps. Like, you don't do that. Nobody does that. You're not supposed to. The documentation doesn't even tell you how inefficient they are at 90 amps, because the designers of like Intersil knows if you're buying those things, you're not going to run 90 amps through them. It's more like a performance class than it is an actual useful specification. But anyway, so yeah, I don't know why they decided to go with the 100. Well, no, I do know, marketing purposes, but I still think this was a very silly decision, because, like, maybe they did actually run a test. I kind of doubt it. Maybe they did have some version, like there was engineering samples of this board with 90 amp power stages, and that ran at the same temperature. Like, well, no, that's the thing. It probably ran at the same temperature. Because like, a small difference in efficiency isn't going to make a huge difference in operating temperature, but still, it's just like, why bother with these? But anyway, the part I find most annoying about these 100 amp smart power stages is that their documentation ends at 40 amps. Yeah. For comparison, 60, 70, and 90 amp parts from the likes of Intersil and Infineon normally go to at least 50. Or 60 amps in terms of like the efficiency curves. These go to 40, which is like, not like, I'm not impressed. I'm really not impressed by that. That has to be the biggest disparity between nominal current spec and then the actual performance curve that you get, right? Because the performance curve for these goes from 0 amps to 40 amps, whereas most of the other power stages are like, they go from 0 to 50, or 0, like most of the other high-end, high current power stages out there go from 0 to 50 or 0 to 60. These go to like 0 to 40, which is just like, I mean, at 40 they're still, perfectly usable, but it's just like stupid 100 amp smart power stages. Anyway, I do still like the board. Like, I just like I can still like the board even if I think the power stage choice is dumb. Like, there's nothing wrong with these. They're perfectly capable of powering anything you put in the socket, but it's just like, why? Why bother? Just use the 90 amp intersills. Actually, they could have used 70 amp parts, and I still wouldn't mind, because it doesn't make a difference. That's the whole issue I have with this, is now we're gonna have, like, I'm sure we're gonna see a motherboard soon enough where somebody digs up like 120 amp power stage, which still isn't any more efficient than the 90s that we already have, but hey, it's a bigger number. Anyway, so yeah, at 1.2 volts output voltage and 600 kilohertz switching frequency, and like the thing is, ultimately, even with these 100 amp smart power stages, like, this is not the most efficient VRM in Gigabyte's lineup. At least, like, well, yeah, it's not the most efficient, because the thing is, one, as I said, the intersil parts, like, I'm going off of the documentation. I don't really have a good way of testing the VRM efficiency, like, at all. There's just really no good way to do that. So I'm just going off of the specifications from the manufacturers, and, like, assuming intersil specifications are comparable to Vishay's, the intersil parts would have been more efficient. And that's kind of like when we do the other Gigabyte boards, you'll notice that, hey, these are all, like, more efficient than the Tachyon. I wonder why that is. Yeah, it's because those all use the 90 amp intersills, and for whatever reason, Gigabyte decided that they really needed to have a 100 amp power stage, so they got one. It's not even spec to 100 amps, but sure. Anyway, so 200 amps output current, this VRM is going to produce about 23 watts of heat, which is kind of high. Like, there's a lot of VRMs out there that'll do 200 amps at less than 20 watts of heat output at 1.2 volts. So, yeah. Now, it's not a problem. The VRM, like, the thing is as I said, like, on paper, this really doesn't look that efficient. So I ended up doing a VRM torture test where I ran Prime 95 on this board for 7 hours with no airflow, but the heatsink still installed, because I didn't really trust the VR. Like, you know, like, I have some faith in Gigabyte's ability to design a VRM, but not enough to, like, run this without the heatsink for 7 hours in Prime 95. And I was running 340 watts of CPU power consumption, which was about 250 amps at 1.35 volts, and that was in a 23 degrees Celsius room. The board ended up at 75 degrees Celsius VRM temperature, so a perfectly acceptable VRM operating temperature, but I really wouldn't take off the heatsink. Because there are other boards that you can totally get away with running no heatsink on them in that kind of scenario, and, like, this should still technically just skirt, like, this would probably end up at around 100 degrees Celsius, which is technically still okay, but not 100% sure. So, like, the thing is, yeah, this is perfectly capable of powering anything you put in the socket. It doesn't overheat or anything, but I don't know why they didn't just use the bloody 90s. Also, on that note, the iGPU VRM does use its own separate voltage controller over here, because the 69269 is a, like, it only goes up to 11 plus 1 here. So for the iGPU, they had to buy an extra controller. I'm not entirely sure why they didn't, like, the issue is, like, with this controller being where it is, you'd have to, like, if you wanted it to control the system agent, you'd have to, like, do something like that, which is bad. You don't really want to be running a PWM line through the memory section of the board, or do this, which, yeah, that's probably not ideal. But I'm not sure why they didn't, like, maybe, like, move the controller over here so that the ISL 69269 could give you a 12-phase V-core, and then you could have your iGPU off of this and your system agent off of this. Because, like, they have the two controllers. Like, this thing goes up to, what is this thing? Also, yeah, we'll get to the current figures later. Anyway, so this thing right here is a RAA. Oh, and I didn't write down how many phases it goes up to. It's got way too many legs to be a single phase controller. I think it's a 6 or a 4. Anyway, that's an yeah, actually, no, that is like that's a 7 or something. I've seen this part number before. This is a relatively high phase count controller. Anyway, that's just running the one phase for the iGPU, which is like, you guys could, like, they could have really run system agent off of that, assuming that like, if the controller was in a different location. Like, basically, the power delivery would probably have to get rearranged a bit to do that, but then they could have squeezed in a 12th V-core phase, which would have slightly improved the efficiency for 200 amps output, but Like it wouldn't be a huge difference, but it's just kind of like, look, if you're going to be digging up 100 amp smart power stages, why, like, you may as well go all the way to 12 phase vCore. Anyway, also I think they actually market the board as having 12 phase vCore, which it isn't, because it's 11 phases for vCore and then one iGPU. But anyway, 253 amps, which seems like a very odd number, but that's because that's where the VRM hits peak efficiency, which conveniently enough is roughly about how much current you can shove into the average LGA 1200 CPU before it gets really difficult to cool it. So yeah, 253 amps, the VRM produces 28 watts of heat. And yeah, like that's completely coolable, which makes, like, as I said, right? Like I ran a 7-hour stress test of Prime 95 and it ended up sitting at 75 degrees Celsius, and it was like, well, yeah, 28 watts of heat spread across this much. Like the VRM itself is spread out quite wide, which is a thermal optimize. Like you'll notice, like, there's big gaps between the inductors. There's a lot of boards where they would just cram the inductors right next to each other. So the board is already, like, you have some thermal optimization by just spacing out the VRM a bit like this. And then, like, the heatsink this board comes with is massive. It's not a very high surface area. Well, it has significantly more surface area than a bare PCB. It's not like it's like some super dense fin stack or anything. It's like it's a really, really heavy block of aluminum, though. And it is huge, so it still does a perfectly good job of cooling the VRM, even in like a zero airflow environment like I was running. So yeah, that's the thing. But on paper, this is not the most efficient VRM that Gigabyte could have put together in this phase count, and most of that's down to the 100 amp smart power stages. At least if the documentation from like Intersil and Vishay is to be believed. Like, one of them is being more optimistic than the other, or it's just like very different test scenarios, and I don't know which one applies better. I really wish there was a 90 amp version of this board, like a Tachyon Lite with the 90 amp parts. It would be hilarious if that ended up running cooler. If I had 2 of these, I would totally consider replacing all of the smart power stages. But I have 1 of these, and these are super rare, so we are not doing that. Like, I'm pretty sure, like, I really want to know, is there, like, because I expect it to go one of 2 ways. Either the 90s from Intersil are actually better, or there is no difference between the 90s and the 100 amp, between the 90 amp parts and the 100 amp parts, in which case, you still have to question, why did they use the hundreds, if the 90s don't perform any differently? Anyway, 300 amps output, this VRM will produce about 34 watts of heat, which, yeah, that, like, on paper, just, I'm annoyed about this. I'm so annoyed about this. Like, like, it performs fine. It's just on paper it looks bad, and I'm not even sure if it's, like, is it a documentation thing? It's probably a documentation thing. Like, I really hope it's a documentation thing. But, yeah, anyway, 400 amps output, 48 watts of heat, and then the fun part where it's like normally for the super high-end Z590 and Z490 boards, I was speccing them out, I think, to 500 amps or something. Yeah, you can't do that with this one because the documentation ends at 40 amps. Again, 100 amp smart power stages, data sheet ends at 40 amps because, like, you're not supposed to run 100 amps through the damn things. And honestly, at 40 amps, with 40 amps flowing through each of these, like, they do get kind of hot because that's 55 watts of heat total from the VRM, which total, like, the thing is, if you're running ambient cooling, you're going to be below 300 amps output current. Actually, I'd be really impressed if you managed to cool 300 amps of power draw on any of the, like, 10th or 11th gen CPUs, because, well, I guess there is the cryo cooler from Intel. So I guess, yeah, you could probably manage 300 amps on that. Actually, no, you couldn't. That would probably overwhelm the Peltier. But anyway, yeah, so you're going to be below the 300 amp mark, and there the VRM performs just fine, even though on paper it doesn't seem to be the most efficient one. Like, it doesn't seem to be the most efficient one. And then from 400 amps up, like, we're talking LN2 overclocking territory. And the funny thing about LN2 overclocking is nobody runs Prime 95 on LN2. So basically the VRM concerns for LN2 overclocking is just like, can the VRM not overheat before the benchmark finishes? And with how incredibly heavy the VRM heatsink for this board is, like honestly, like for most benchmarks finish so quickly, you can just run the VRM naked with no heatsink whatsoever. And if for some reason you are running a benchmark that is all core load for like multiple minutes, you'd probably need like 10 minutes of all core load before this overheats. Like it would take a while. So assuming you did find a benchmark that for some ungodly reason you're running long enough to actually run into potential VRM thermal issues, if you put the VRM heatsink back on, it's going to be fine. It's not going to be a problem anymore. So yeah, this is not the most efficient VRM in Gigabyte's lineup, and it's not the most powerful VRM in Gigabyte's lineup, but it is certainly capable of powering anything you could put in the LGA 1200 socket, which is why, even though, like, I know I've just been very negative about these 100 amp smart power stages, because I do believe, like, I still think they're stupid. And like, unless somebody shows me a thermal test of like these 100 amp parts compared to the 90 amp intersills, where it's like these actual, like these perform at least the same, if not better, then, yeah, like I'm just gonna like keep complaining about them because it's just use the bloody 90s. It would have made the board cheaper probably, because they're already buying so many of the 90s anyway. Where was I going with this? Yeah, so I'm not a fan of the 100 amp smart power stages, and the VRM like on paper isn't the most efficient. But the thing is, the VRM just needs to be capable of powering anything you can put into the socket. So as much as I've been complaining about this whole VRM here, I still think this, like, I still consider this the great, like, the best motherboard I've ever used, because yeah, I think some of the design decisions might not have been completely optimal here, but like, I don't have hard proof of that. So that's mostly like an opinion thing, right? Like, again, the data, like, the data sheets aren't solid proof that in this specific application the 90s wouldn't necessarily, like, the 90s might not be better in this specific application. But yeah, so it's just kind of me complaining. So where was I going? I still like the board. There, that's what I'm trying to say. Man, this video, this board. Like, if Gigabyte just used the 90s, my life would have been so much easier. Because I saw the document, like, I've had the script written for this for so long, and this part of the video has just been like, I have no idea. Because there's boards that I remember doing videos for where you'd have 200 amps at like 16 watts of heat output, going by the specifications from the manufacturer. And then there's this board where it's like, well, if I look at Vishay's data sheet, it says it's going to do this. Like, what am I supposed to do about that? Right? And initially I thought, oh, maybe it's because like they're comparing full converter efficiency versus just power stage efficiency, but no. No. Intersil, like, that's the same between at least the Intersil and the Vishay data sheet. And so it's just like, ah, yay, yeah, this is great. I have no idea what to say about this, which is why I ended up doing the thermal test, because it's like, yeah, like in practice this performs just fine, but yeah, on paper it really, it's on paper it's not very impressive, unfortunately. So yeah. Anyway, moving on to the memory configuration. We've got 2 DIMM slots, so one DIMM per channel, and then we've got full, full ground fill over all of the memory traces for shielding, and you can see all the stitching of the ground fill running along the edges. So that's basically just to improve the signal integrity of the memory on the board, and like, I've done some memory overclocking on this board. It seems pretty good. I'm not sure, like I've not run A/B comparisons between boards, and the thing is, a lot of the memory overclocking also really depends on the BIOS optimizations of the motherboard. So the topology, the topology plays a role, but the BIOS also plays a very big role. So yeah, it's too early to judge that, in my opinion, because for 11th gen the BIOSes are still being tweaked in many ways. So Yeah, but, you know, 1 DIMM per channel with full ground shielding, and this is a 8-layer PCB. There's a little layer count indicator down there. So, yeah, and then actually Gigabyte went for the pulse caps in the memory VRM as well, which I find really surprising, but also what I find absolutely hilarious is I'm pretty sure these capacitors cost more than like all of the MOSFETs and the inductor and the controller for the VRM. Because this is the same control, like it's the same controller and it's the same MOSFETs that you would find even on like the, well, no, I think some of the super low end Gigabyte motherboards get rid of the second low side MOSFET. But yeah, like Gigabyte uses this memory VRM configuration everywhere. So yeah, I find that absolutely hilarious that we have these super expensive capacitors whacked onto like what, well, like you it's not the cheapest, but like a not like a very basic memory VRM. And the thing is, you don't need, like, DDR4 doesn't pull enough power to justify using like power stages for it. So I have no problem with them doing this. I just think it's really funny that you've got these really, really high-end capacitors and then like these MOSFETs. Because that's a 4C10N and then a bunch of 4C. Actually, I think it might be all 4C06s. I can't remember, but they're not particularly great MOSFETs. And yeah, on the back, again, you know, full shielding, so you can't see any of the memory traces. And yeah, so that is the Z590 Tachyon. My, like, probably favorite, well, currently my favorite motherboard of all time. It's just a real shame that Gigabyte made it so hard for me with this video and their stupid 100 amp power stages. I still don't get why they're nominally spec to 100 amps, especially considering that the like efficiency curve ends at 40. Yeah. Anyway, so I'm kind of annoyed that I have to use like I have this board and all the other Z590 Gigabyte boards because I don't really want to use the others. Because yeah, this thing is so nice. Like the limp mode button, and really like this section, this section of the board is just awesome. And then of course, like the VRM itself is also just fine. I still need to run oscilloscope tests on it, but like it's at least gonna be it's gonna have at least the same performance as the Z490 boards. And if it's better, then I'm going to be really impressed because I like looking at the Z490 test results. It's been like, there's no way you can get a better transient response performance than what the Z490 boards were doing. But hey, maybe this does manage better, in which case I'm still not over the 100 amp smart power stages. Like, like, yeah, I don't know. Like, this video is going nowhere, so I guess we'll just end it here. I really wish this could have been more, like, I really, really wanted this whole video to be positive, but there's just nothing I can do about the fact that, like, Gigabyte found a 100 amp smart power stage in, like, Visay's couch or something, and the spec sheet for it looks absolutely bloody horrendous. Okay, it's not that bad. Like, it's still a perfectly good smart power stage. It's just, like, it's not better than the 90s from Intersil or Infineon or any of the other 90 amp smart power stages I've seen from anyone. So why? But anyway, yeah, that's it so I guess thanks for watching. Like, share, subscribe, and leave any comments or questions down in the comment section below. And if you'd like to support what I do here with actually hardcore overclocking, I have a Patreon where you can support me directly. There's a link to that down in the description below. And then there's also the AHOC Teespring store where you can pick up shirts, stickers, posters, you know, the usual YouTuber merch. There's a link to that down in the description below as well. And yeah, that's it for this video. Hopefully Gigabyte keeps sending me boards. Like, stupid 100 amp smart power stages. I'll go stop the video.